Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete history, meaning, and function of one of the most fundamental building blocks of the digital world, bits and bytes. This narration is intentionally slow, detailed, and repetitive. It is designed to help you relax, focus, or gently fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information, spoken at a calm and consistent pace. You do not need to remember every detail, because the story will unfold carefully, one idea at a time. Now, please sit back, close your eyes if you wish, and allow the quiet journey into the world of bits and bytes to begin. When we begin to explore the world of bits and bytes, it is important to first understand the broader concepts of information and data, since they form the foundation of everything that follows. Information is something that humans interpret and give meaning to, while data is the raw material that computers process. Imagine information as knowledge or a message, and data as the symbols, numbers, or characters that are used to transmit this knowledge in a structured way. For centuries, humans have looked for ways to record, store, and transfer information, from spoken language to written texts, from printed books to digital files, and every step along the way has been about making information more accessible and easier to preserve. In the digital age, we often use the term data when we talk about files, images, videos, or programs, but these are all built from the smallest possible units of digital representation. Information that we see on our screens, such as a picture or a document, might look smooth and continuous to our eyes, but underneath it is structured in a precise way, using tiny building blocks that can be managed by machines. These building blocks are what we call bits and bytes, and understanding them allows us to grasp the logic of how computers and digital devices function. The concept of information has always been about reducing uncertainty. If someone tells you the result of a coin flip, they are providing information, because before hearing it, you did not know whether the coin showed heads or tails. In computing, the smallest way to represent such a two-choice outcome is with a single unit called a bit. A bit can have only two possible values, traditionally expressed as 0 or 1. Before diving into bits directly, however, we need to appreciate that all digital information must first be translated into data that can be handled by machines, and the bit is the smallest meaningful symbol in this translation. Data, in its essence, is a representation of facts, measurements, or instructions that can be stored and transmitted. A photograph stored on your computer is not the actual picture in the physical world, but rather a very large collection of data points that represent light intensity and color at each position. A song you listen to is not sound waves traveling in the air, but a sequence of data samples that a device interprets and converts back into sound. All of these examples highlight that data is a structured representation, and information is the meaning we humans assign to it. The separation between data and information is essential to avoid confusion, because machines only work with data, while humans ultimately seek information. In modern computing, data is processed and transmitted in binary form, which means it is broken down into sequences of zeros and ones. This binary representation is the simplest way to store information reliably, because it maps naturally onto physical systems that can have two stable states. Early engineers discovered that electrical circuits could be built in such a way that they either carried current or did not, and this clear distinction made it possible to use them as carriers of binary values. A voltage might represent a 1 and the absence of voltage a 0. With this foundation, the entire digital revolution became possible. To fully appreciate what bits and bytes are, we must understand that they do not exist in isolation, but are embedded in larger frameworks of data processing. A single bit by itself does not carry much information. Knowing whether a single switch is on or off only tells us about two possible states. However, when multiple bits are combined, the number of possible states increases exponentially. 2 bits together can represent 4 possible states, 3 bits can represent 8, and so on. By the time we group 8 bits, which we call a byte, we can represent 256 possible states. This grouping into bytes makes it practical for computers to work with larger ranges of values, which can then correspond to letters in the alphabet, colors in an image, or instructions in a program. The importance of understanding information and data at this fundamental level lies in realizing that every digital experience we have is nothing more than combinations of bits and bytes. Whether you are watching a movie, browsing the internet, or writing a text message, everything is stored, transmitted, and processed as data. Without the abstraction provided by bits and bytes, our modern digital world would not be possible. By reducing the complexity of reality into structured data, computers allow us to create, store, and share information at a scale never before imaginable. The journey from the abstract concept of information to the physical implementation of data in machines is one of the greatest achievements of human ingenuity. It required not only philosophical reflection on the nature of knowledge, but also practical engineering to make information manageable by physical devices. The recognition that all forms of human expression could be reduced to patterns of bits and bytes reshaped the 20th century and continues to define our era. When you open a simple text file, it may appear to you as letters and sentences, but beneath the surface, the computer sees it only as sequences of zeros and ones. This invisible translation is what makes the entire digital ecosystem function, and it is why the study of bits and bytes begins with a deep understanding of information and data. To understand why bits are so essential in the world of computing, it is necessary to examine the binary system itself, which serves as their foundation. The binary system is a method of representing numbers, symbols, and operations using only 2 distinct states, usually labeled as 0 and 1. While humans are most familiar with the decimal system that is based on 10 digits from 0 to 9, computers rely on binary because it aligns perfectly with the physical limitations of electronic devices. An electrical circuit can either carry current or not. A switch can be either open or closed, and a magnetic surface can be oriented in one direction or another. These 2 stable and easily distinguishable states provide the perfect basis for storing and processing information in machines. In the decimal system, the value of a number is determined by the position of each digit, where each position represents a power of 10. For example, the number 345 means 3 hundreds, 4 tens, and 5 ones. Similarly, in the binary system, each position represents a power of 2 rather than a power of 10. The binary number 1011, for instance, represents 1 times 2 to the power of 3, plus 0 times 2 to the power of 2, plus 1 times 2 to the power of 1, plus 1 times 2 to the power of 0. That calculation results in 8 plus 0 plus 2 plus 1, which equals 11 in decimal notation. Through this positional structure, binary numbers can represent any quantity, even though they use only two symbols. The strength of the binary system lies in its simplicity and reliability. While humans might find it easier to work with decimal numbers in daily life, computers benefit enormously from having to distinguish only between two possibilities. By avoiding the complexity of multiple states, errors are reduced, and signals can be processed more quickly and consistently. It is far easier for a circuit to determine whether there is voltage or no voltage than to try to distinguish between 10 different voltage levels corresponding to the digits of the decimal system. The binary system therefore represents a natural fit between the abstract needs of information processing and the physical properties of electronic systems. The concept of base systems is not unique to binary and decimal. Humans have historically used other number systems as well. For example, the ancient Babylonians used a base 60 system, which still influences how we measure time in minutes and seconds. In computing, however, binary reigns supreme, although hexadecimal or base 16 is often used as a shorthand for binary because it is more compact. Each hexadecimal digit corresponds exactly to 4 binary digits, making it much easier for programmers and engineers to read and write long binary sequences without losing track. Nevertheless, beneath every higher level representation lies the simple structure of binary digits, the fundamental zeros and ones. Binary logic extends beyond just representing numbers. It forms the foundation of logical operations that computers use to make decisions and perform calculations. Using binary values, we can define operations such as and, or, and not, which describe how different binary inputs combine to produce specific outputs. For instance, an AND operation takes 2 input bits and produces a 1 only if both inputs are 1. These logical operations can be physically realized with electronic gates that respond to electrical signals. By combining large numbers of such gates, engineers can design circuits capable of performing complex tasks, from adding numbers to running entire programs. When you look at a computer executing sophisticated software, it might be difficult to imagine that everything is ultimately built upon binary operations. However, every line of code, every graphical display, and every sound output can be traced back to sequences of zeros and ones being manipulated through logical rules. This universality of binary logic is what allows computers to be general-purpose machines. They are not limited to one type of calculation, but can, in principle, simulate any process that can be described in binary form. This idea was formally captured in the concept of the Turing machine, which demonstrated that a simple device operating on binary symbols can compute anything that is computationally possible. Binary representation also ensures that data can be stored and transmitted in highly efficient ways. A single bit can represent the result of a yes or no question, while larger groups of bits can represent numbers, letters, or even entire instructions for the processor. When multiple bits are used together, the expressive power of the system expands dramatically. For example, a single byte of 8 bits can represent 256 distinct values, which is enough to encode all the characters in the English alphabet, along with numbers and symbols. With larger groups of bits, entire multimedia files, complex applications, and operating systems can be represented. What makes the binary system so profound is that it bridges the gap between abstract mathematics and physical reality. Mathematics provides the rules for manipulating binary numbers and performing logical operations, while physics and engineering provide the means of implementing these rules in circuits, transistors, and memory devices. This interplay between theory and practice has driven the rapid development of computing technology over the past century. Without the binary system, it would have been impossible to scale computing power to the levels we see today, where billions of transistors in a microprocessor operate together to handle massive amounts of binary data. The binary system also reveals something deep about the nature of information itself. At its most basic, information can be reduced to a distinction between two alternatives. Whether it is yes or no, true or false, on or off, the binary system provides the minimal language necessary to capture such distinctions. By chaining together countless binary decisions, it is possible to describe incredibly rich and complex structures, from the genetic code of life to the instructions that power modern artificial intelligence. In this way, the binary system is not just a convenience for engineers, but a fundamental way of structuring information about the world. As we proceed further into the digital age, the binary system continues to remain the unshakable foundation of computation, communication, and data storage. Even as new technologies such as quantum computing emerge, they still relate back to the binary framework, since quantum bits are described in terms of superpositions of 0 and 1. This demonstrates the universal power of the binary system to model and process information at all scales. By understanding how binary works, we gain insight not only into how computers operate, but also into the essence of information itself, which always begins with the simple yet profound choice between two possibilities. When discussing the digital world and how machines operate, the most fundamental unit to consider is the bit. The bit, short for binary digit, represents the smallest piece of data in computing. It has only two possible values, typically written as 0 and 1. This might sound incredibly simple, almost too simple to form the foundation of the vast digital landscape. But it is precisely this simplicity that makes the bit so powerful and universal. By limiting itself to two values, the bit can be reliably stored, transmitted, and manipulated by physical systems, which inherently work best with two distinct states, such as on and off, high voltage and low voltage, or magnetized and demagnetized. A single bit by itself may not appear to carry much information. For example, if you flip a switch, the outcome is either on or off, and this mirrors the two values of a bit. However, when multiple bits are combined, their ability to represent information grows exponentially. 2 bits can represent 4 states, 3 bits can represent 8 states, and so forth. By the time you reach 8 bits, which form 1 byte, there are 256 possible combinations. This exponential growth explains why bits are so effective in representing a wide range of information, from simple instructions to complex data structures. The role of a bit is not only to represent information, but also to act as the building block for all higher-level operations in computing. When you type a letter on your keyboard, it may look like a character to you, but for the computer, it is a combination of bits. The ASCII system, one of the earliest standardized methods for encoding text, uses 7 or 8 bits to represent characters such as letters, numbers, and punctuation marks. In this way, the bit becomes the bridge between human-readable symbols and machine-readable code. Every file on a computer, no matter how sophisticated it seems, is ultimately a long sequence of bits interpreted according to a specific set of rules. In addition to representing characters, bits are essential for representing numbers. In binary notation, the sequence of bits corresponds to powers of 2, allowing for any integer to be expressed. For instance, the number 13 in decimal is represented in binary as 1101, meaning 1 times 2 to the power of 3, 1 times 2 to the power of 2, 0 times 2 to the power of 1, and 1 times 2 to the power of 0. This straightforward system means that bits can handle not just the storage of numbers, but also the performance of arithmetic operations. Modern processors contain millions or billions of transistors that switch states rapidly, manipulating bits in order to carry out complex calculations at incredible speed. The concept of a bit extends beyond storage and arithmetic to logical decision-making. A bit can represent the outcome of a logical condition, such as whether something is true or false. In programming, these conditions are fundamental to decision-making. For example, a program may test whether a value is greater than another, and then set a bit to 1 if it is true, and 0 if it is false. These binary outcomes allow software to control processes, repeat actions, or branch into different operations. Once again, the bit is at the heart of how the machine reasons and makes decisions. Bits also play a crucial role in communication systems. When you send a message over the internet, the data is broken down into bits that are transmitted through physical mediums such as fiber optics, copper wires, or wireless signals. These bits travel as light pulses, electrical charges, or radio waves, and at the receiving end, they are reassembled to reconstruct the original data. The robustness of binary representation ensures that even in noisy environments, bits can be transmitted reliably with the help of error detection and correction techniques. The digital nature of communication owes its resilience to the simplicity of the bit, since distinguishing between two clear states is far easier than maintaining many different states over long distances. The measurement of data capacity and speed is also defined in terms of bits. Storage devices, such as hard drives and memory chips, are rated according to how many bits or bytes they can hold, while network speeds are often measured in bits per second. A gigabit per second means 1 billion bits transmitted every second. This shows that even when dealing with vast amounts of information, the unit of measurement always returns to the bit, reminding us that every large-scale digital process is composed of countless tiny binary steps. It is also important to recognize the symbolic meaning of the bit in computer science. The bit is not merely a technical unit. It represents the very philosophy of digital information. By reducing all possible data into a combination of zeros and ones, the bit embodies the principle of abstraction, where complex phenomena are broken down into their simplest possible representations. This abstraction allows computers to model anything that can be expressed symbolically, from mathematical formulas to images, from sound to video. The bit is therefore not just a unit of data, but also a conceptual tool that enables universal computation. While a single bit may seem trivial, the aggregation of bits allows for extraordinary complexity. When billions of bits are stored and processed every second, entire virtual worlds, global communication networks, and advanced artificial intelligence systems become possible. The power of the digital age rests on the reliability and universality of the bit. Every device we use, whether a smartphone, a laptop, or a supercomputer, is built upon the same humble building block. By grasping the definition and role of a bit, one begins to appreciate the elegant simplicity that underlies the apparent complexity of modern computing. The story of the bit is ultimately the story of how humanity found a way to tame information and make it manageable by machines. It demonstrates how two simple symbols, 0 and 1, can be combined in countless ways to represent knowledge, perform reasoning, and enable communication. As we continue to advance technologically, the bit remains at the center, ensuring that no matter how complex our systems become, they are always grounded in the fundamental logic of binary choices. This enduring role makes the bit not only the smallest unit of digital data, but also the most important concept in the digital universe. In the world of digital technology, the concept of bits alone is not sufficient to handle the vast amount of information that must be processed, stored, and transmitted. While a single bit can express one of two states, its usefulness grows exponentially when bits are grouped together. The most common grouping is 8 bits, which form a byte. The byte has become the standard unit of digital data, and it plays a central role in computing, communication, and storage. To understand the practical meaning of bytes, it is necessary to explore how bits combine to create meaningful representations, how these groupings are standardized, and how they are used in everyday applications. When we speak of a byte, we are referring to a collection of 8 bits, each of which can be 0 or 1. With 8 positions, the number of possible combinations is 2 raised to the power of 8, which equals 256. This means that a single byte can represent 256 distinct values. Such a range is sufficient to encode letters, numbers, punctuation, and control characters, which is why bytes quickly became the standard building block for representing text and symbols in computer systems. The ASCII code, one of the earliest encoding systems, mapped characters such as the letter A or the number 7 to specific byte values, making it possible to exchange text between machines and humans in a reliable and standardized way. The introduction of the byte also simplified data storage and memory management. Instead of thinking in terms of individual bits, which would be cumbersome and difficult to manage, computers began organizing data in units of bytes. Memory chips, hard drives, and file systems measure their capacity in bytes, kilobytes, megabytes, gigabytes, and beyond. Each step up represents a power of 2, with a kilobyte equaling 1024 bytes, a megabyte equaling 1024 kilobytes, and so forth. These larger units are nothing more than convenient groupings of bytes, but they allow us to describe and handle massive amounts of data in a manageable way. The practical meaning of bytes becomes clear when we consider how they represent everyday information. A simple text document might require a few kilobytes of storage, since each character requires 1 byte. A small image may require several hundred kilobytes, because each pixel's color value is represented by multiple bytes. A digital song may take up a few megabytes, while a full-length movie in high definition might require several gigabytes. The byte is therefore the link between the smallest building block of binary data and the large, complex files we use daily. It serves as the fundamental currency of the digital world, and all higher-level operations ultimately depend on the manipulation of bytes. Beyond storage, the byte is also essential in communication. Network protocols are designed to transmit data in packets, which are sequences of bytes. When you send an email, stream a video, or download a file, what actually happens is the transmission of millions or billions of bytes across networks. Each byte carries a portion of the information, and the receiving system reconstructs the original file by reassembling the bytes in the correct order. The reliability of communication depends on ensuring that every byte arrives intact, which is why error detection mechanisms, such as checksums and parity bits, exist to verify the integrity of transmitted data. The role of the byte extends into computer architecture as well. Most modern processors are designed to handle data in units of bytes or multiples of bytes. Instructions are written with the assumption that data is organized in this way, and memory addressing is typically byte-oriented, meaning each memory location stores one byte. This design choice makes it easier to align hardware and software, ensuring consistency across different levels of a computing system. The byte thus represents a natural compromise between the minimalism of bits and the practicality of handling larger units of data. One of the fascinating aspects of the byte is its universality across different forms of digital content. Whether you are dealing with text, images, audio, or video, everything reduces to bytes. A photograph is nothing more than an arrangement of bytes that describe color and brightness values for each pixel. A song is a sequence of bytes that represent sound wave samples. A video combines both images and audio into an even larger sequence of bytes. Even executable programs, which direct a computer's actions, are simply bytes arranged according to specific instructions that the processor can interpret. This universality underscores the elegance of digital systems, where all complexity arises from the simple combination of bits into bytes and bytes into larger structures. The practical meaning of bytes also extends to the user's perception of digital technology. When you check the size of a file on your computer, you see it measured in kilobytes, megabytes, or gigabytes. When you subscribe to an internet service, the speed is advertised in megabits per second, which, though slightly different from megabytes, still refers back to the fundamental concept of bits and bytes. The entire digital economy, from cloud storage to mobile data plans, is built upon the quantification of information in these units. Consumers may not always think about the underlying bits and bytes, but every interaction with digital devices involves them. Furthermore, bytes allow standardization across systems and platforms. Because the byte is universally recognized as the fundamental unit of data, different devices can exchange information without ambiguity. A byte on a smartphone has the same meaning as a byte on a supercomputer. This consistency ensures compatibility and interoperability, enabling the global digital infrastructure to function smoothly. Without such standardization, communication between devices would be chaotic and unreliable. Ultimately, the transition from bits to bytes illustrates the human capacity to organize simplicity into complexity. A bit on its own is almost trivial, but bytes transform these simple binary digits into something useful and practical. The byte serves as the interface between the abstract binary world of machines and the tangible digital content we interact with every day. By grouping bits into bytes, engineers created a scalable, flexible system capable of handling everything from the smallest text files to the largest scientific simulations. The byte is therefore not only a technical unit, but also a profound symbol of how order emerges from simplicity, demonstrating the elegance and power of digital design. The story of bits and bytes is deeply tied to the history of computer science, and it illustrates how abstract concepts of information were transformed into practical tools that now define the modern world. The journey begins long before the invention of electronic computers, when early thinkers began exploring how information could be represented symbolically and mathematically. One of the earliest contributors to this line of thought was the mathematician and philosopher Gottfried Wilhelm Leibniz in the 17th century. Leibniz developed the binary number system, arguing that all numbers could be represented using only two digits, 0 and 1. For him, binary was not only a mathematical curiosity, but also a philosophical expression of the universe being composed of opposites, such as existence and non-existence. Although his ideas were not immediately applied to machines, they laid the groundwork for the concept of bits centuries later. The 19th century brought further developments in symbolic representation with the invention of the telegraph and other communication technologies. The Morse code, for example, reduced letters and numbers to sequences of dots and dashes, which can be seen as an early attempt to encode information in a binary-like fashion. Each dot or dash could be transmitted reliably over long distances using electrical pulses, similar to the way computers later used bits. These innovations demonstrated the practicality of reducing complex information to simple signals, paving the way for the eventual dominance of binary logic. In the early 20th century, engineers and mathematicians began to see the potential of binary systems in computation. Claude Shannon, often called the father of information theory, played a decisive role in formalizing the bit as the unit of information. In his groundbreaking 1948 paper, A Mathematical Theory of Communication, Shannon introduced the concept of measuring information in terms of binary decisions. He showed that every message, no matter how complex, could be broken down into a sequence of yes or no choices, or bits. Shannon's work not only gave birth to the bit as a scientific concept, but also demonstrated its practical relevance to communication systems, laying the foundation for digital data transmission. While Shannon was shaping the theoretical side of information, engineers were building machines that could implement binary logic. Early computers such as the ENIAC were initially decimal-based, relying on more complex electronic designs. However, as technology advanced, engineers quickly realized that binary systems were far simpler and more reliable. The use of vacuum tubes, and later transistors, made it practical to design circuits that represented data as on or off states. This shift marked the true beginning of bits and bytes as the universal language of computing. By the 1950s and 1960s, binary architecture became the standard design principle for computer systems worldwide. The concept of grouping bits into bytes also emerged during this period as computing moved from theory to practical application. Early machines often had different word lengths, meaning the number of bits processed together could vary. Some used 6-bit units, while others used 9-bit units, depending on the design. Eventually, the 8-bit byte became standardized because it provided enough combinations to represent a wide range of characters, while still being manageable in terms of memory and hardware design. This standardization allowed for greater compatibility between systems and accelerated the growth of computer science as a unified field. As computing spread into different industries, the role of bytes became even more significant. Text processing systems needed standardized ways to represent letters, which led to the development of ASCII in the 1960s. ASCII mapped characters to byte values, making it possible for different machines to exchange text without confusion. This marked a turning point in the practical application of bytes, as they became the universal carriers of symbolic information. The influence of ASCII persists even today, as modern encoding systems, such as Unicode, still rely on the byte as the fundamental unit. The historical development of bits and bytes also reflects the rapid evolution of storage and communication technologies. In the earliest computers, storage was extremely limited, and programmers had to make careful decisions about every bit used. A single byte might represent an entire instruction in a program. Over time, advances in memory and storage capacity allowed for more complex uses of bytes, enabling the growth of software industries, multimedia applications, and eventually the Internet. Each leap in technology, from magnetic tapes to solid-state drives, relied on the efficient representation and manipulation of bits and bytes. Networking also played a major role in demonstrating the power of bits and bytes. In the 1970s and 1980s, the development of data transmission protocols such as TCP/IP enabled computers to exchange information across networks. These protocols defined how sequences of bytes were packaged into data packets, transmitted across different physical media, and reassembled at the destination. The Internet, as we know it, would not exist without this precise management of bytes, which allowed global communication to scale from a few research institutions to billions of devices worldwide. The cultural meaning of bits and bytes also grew during this historical period. As personal computers became common in the 1980s and 1990s, users began to think of files, programs, and media in terms of kilobytes, megabytes, and eventually gigabytes. The language of bits and bytes entered everyday vocabulary, symbolizing the digital nature of modern life. This shift demonstrates how an abstract mathematical idea from the 17th century evolved into a practical framework that now structures our daily experiences. Today, the historical development of bits and bytes continues with new frontiers in computing. While the bit remains the basic unit, researchers are exploring quantum bits, or qubits, which can exist in superpositions of 0 and 1. Although this represents a radical departure from classical bits, it still builds upon the same history of reducing information to binary states. The journey from Leibniz's philosophical reflections to Shannon's information theory, from early vacuum tube computers to global internet infrastructure, shows how the simple idea of bits and bytes shaped the modern technological world. The history of bits and bytes is therefore more than a technical story. It is a narrative about how humanity discovered that complexity can be reduced to simplicity, and how that simplicity can be scaled to create entire civilizations of digital interaction. Bits and bytes embody the human drive to systematize, to standardize, and to communicate. Their development reflects the intersection of mathematics, engineering, and culture, and their legacy will continue as long as humans rely on machines to process and transmit information. The role of bits and bytes becomes particularly clear when we examine how memory and storage are measured in computing. Every device we use, whether a simple calculator, a smartphone, or a supercomputer, depends on its ability to store and retrieve information. This storage relies on organizing bits and bytes into structured forms that can be accessed efficiently. At the most basic level, memory and storage are quantified by the number of bits they can hold. But because single bits are too small to be practical, larger units such as bytes, kilobytes, megabytes, gigabytes, and beyond are used in everyday language. Understanding these units not only clarifies how computers function internally, but also explains the sizes and capacities we encounter when dealing with digital files, applications, and networks. To begin with, a byte, composed of 8 bits, is considered the standard unit of measurement for memory and storage. Every character in a text file, every pixel in an image, and every instruction in a program can be reduced to a collection of bytes. Once we scale beyond the single byte, we enter the realm of larger units. 1 kilobyte is defined as 1024 bytes because computers operate in powers of 2, while the decimal system would suggest that a kilobyte should equal 1000 bytes. Binary logic dictates otherwise, making 1 kilobyte equal to 2 to the power of 10 bytes. This pattern continues upward. 1 megabyte equals 1024 kilobytes. 1 gigabyte equals 1024 megabytes, and 1 terabyte equals 1024 gigabytes. These exponential increases reflect how quickly capacities grow as we climb the hierarchy of measurement. Memory in computers refers to the temporary storage used while the system is running. Random access memory, or RAM, is a key example. RAM is measured in gigabytes today, but each gigabyte is ultimately billions of bytes, which means billions of sequences of 8 bits. When an application runs, it loads instructions and data into RAM, where the processor can access it quickly. The measurement of RAM in gigabytes tells us how much data the system can handle actively at one time. A device with 4 gigabytes of RAM can store about 4 billion bytes of data in its working memory, while a device with 16 gigabytes can hold 4 times that amount. This difference directly affects performance, since more memory allows more programs to run simultaneously without slowing down. Storage, in contrast, refers to the long-term retention of data, even when the computer is turned off. Hard drives, solid-state drives, memory cards, and optical disks are all forms of storage, and their capacities are also expressed in bytes and their larger multiples. A 1 terabyte hard drive, for example, holds about 1 trillion bytes of data, which can be used for operating systems, applications, media, and personal files. The ability to scale storage from a few megabytes in early computers to several terabytes in modern devices highlights the importance of bits and bytes as universal units of measurement. One interesting aspect of storage measurement is the difference between how manufacturers and operating systems report capacities. Manufacturers often use decimal prefixes, where 1 kilobyte equals 1000 bytes, 1 megabyte equals 1 million bytes, and so on. Operating systems, however, traditionally use binary prefixes, where 1 kilobyte equals 1024 bytes. This discrepancy explains why a hard drive advertised as 500 gigabytes might appear as slightly less when viewed in a computer's file system. To address this confusion, terms such as kibibyte, mebibyte, and gigabyte were introduced to denote the binary multiples explicitly. But in practice, most people continue to use kilobyte, megabyte, and gigabyte in everyday language. The measurement of storage also determines how we experience digital content. A text document might require only a few kilobytes, because each character is a byte, and documents rarely exceed thousands of characters. An image, however, requires far more space, since every pixel must be represented by multiple bytes to capture color and brightness. A high-resolution photograph might easily require several megabytes of storage. Audio files, which store thousands of sound samples per second, can take up megabytes for a single song. Videos, combining both audio and image data, are among the largest files, often requiring gigabytes for a single film. The byte-based measurement system therefore provides a universal way to quantify everything from the smallest note to the largest cinematic production. Beyond personal devices, data centers, and large-scale computing infrastructures also rely on bit and byte measurements. The servers that power cloud services store petabytes and even exabytes of data, each level representing 1,000 times the previous one. A petabyte equals about 1 million gigabytes, and an exabyte equals about 1 billion gigabytes. These colossal figures highlight the scale of modern data storage, where billions of users upload photos, videos, and documents daily. Yet, at the core of this seemingly endless capacity, everything is still counted in bits and bytes. Another dimension of memory and storage measurement is data transfer speed. Network speeds are often expressed in bits per second rather than bytes. For example, an internet connection might advertise 100 megabits per second, which equals about 12.5 megabytes per second. The distinction between bits and bytes in this context is crucial for users to understand, because it determines how quickly files can be downloaded or uploaded. Confusion arises when people mistake megabits for megabytes, leading them to overestimate the speed of their connection. Clear understanding of bits and bytes helps avoid such misunderstandings and ensures realistic expectations. Error detection and reliability are also part of storage measurement. Each byte not only represents data, but can also be used to store information about the integrity of that data. Systems often add extra bits, known as parity bits or checksums, to verify that stored or transmitted bytes remain correct. These practices demonstrate how bits and bytes are not merely static units, but active participants in ensuring that memory and storage systems function accurately. Ultimately, the measurement of memory and storage through bits and bytes illustrates the universality of digital information. Whether dealing with a small handheld device or a massive supercomputer, the language of bits and bytes remains constant. They allow us to describe capacities ranging from the most modest kilobyte to the incomprehensible scales of exabytes. This consistency provides the foundation for the digital world, where every application, every file, and every network connection is quantified in the same units. By understanding how memory and storage are measured through bits and bytes, one gains not only technical knowledge, but also a deeper appreciation of how simplicity enables complexity in computing. The transmission of data is one of the most important functions of modern computing, since devices are rarely isolated anymore. Whether it is a smartphone sending a message, a computer streaming a video, or a server transmitting information across continents, all of these processes rely on the careful handling of bits. The bit, as the smallest unit of data, is the element that makes communication possible in digital systems. To understand its role, it is necessary to explore how data is broken into bits, how those bits travel across different physical media, how they are reassembled at the destination, and how reliability is maintained despite noise and distance. When information is prepared for transmission, it must first be converted into a sequence of bits. A text message, for example, is encoded into bytes using a character encoding system such as UTF-8. Each byte then breaks down into 8 bits. These bits are organized into packets, which are structured groups of data that include not only the message itself, but also control information, such as the source, destination, and error-checking codes. The packet is the fundamental unit of communication, and within it, the bit is the atomic element. Every packet transmitted across the internet is ultimately a long sequence of zeros and ones, traveling from one device to another. The physical journey of bits depends on the medium. In wired systems, bits may be transmitted as electrical signals through copper cables. A high voltage might represent a 1, while a low voltage represents a 0. In fiber optic systems, bits travel as light pulses, where the presence of a pulse may represent one state and its absence another. In wireless systems, bits are transmitted as radio waves, with changes in frequency, amplitude, or phase encoding the difference between 0 and 1. In every case, the binary nature of the bit ensures that signals can be distinguished reliably, even across long distances or in environments with interference. Once bits are transmitted, they must be reassembled correctly at the receiving end. Communication protocols govern this process. Protocols such as TCP, the Transmission Control Protocol, ensure that packets arrive in order and without errors. If some bits are corrupted or lost during transmission, the protocol requests a retransmission. This guarantees reliability, which is essential for applications like file downloads or secure communication. Other protocols such as UDP, the User Datagram Protocol, emphasize speed over reliability, allowing bits to arrive with less certainty, but much faster. This is suitable for applications like streaming video, where slight errors are acceptable as long as the overall flow of data is uninterrupted. Error detection and correction mechanisms play a crucial role in ensuring the accuracy of transmitted bits. One common technique is the use of parity bits. A parity bit is an additional bit added to a group of data bits, designed to make the total number of ones either even or odd. When the data arrives, the receiver checks the parity to verify whether an error occurred. More advanced methods, such as cyclic redundancy checks, calculate mathematical summaries of the data and attach them to the packet. The receiver recalculates the summary and compares it to the transmitted one. If they differ, it means that some bits were altered during transmission. By adding these extra layers of verification, systems can ensure that bits maintain their integrity across networks. The speed of data transmission is also measured in terms of bits. Network speeds are usually described in bits per second, often scaled to kilobits, megabits, or gigabits per second. This unit reflects how many bits can be transmitted in a given time frame. For instance, a broadband connection of 100 megabits per second can theoretically transmit 100 million bits each second. This measurement allows users to compare the capacity of different networks and predict how quickly data, such as files, songs, or videos, will reach them. By expressing speeds in bits rather than bytes, communication systems emphasize the fundamental role of bits as the raw units of transmission. Different layers of communication systems handle bits in specific ways. At the lowest level, the physical layer deals directly with signals that represent bits. Above that, the data link layer organizes bits into frames and ensures they travel reliably between two directly connected devices. Higher layers, such as the transport and application layers, treat bits as structured messages, ensuring that they reach their ultimate destination and can be interpreted meaningfully. Despite these different levels of abstraction, bits remain the common thread binding the entire communication process together. Bits also enable encryption, which protects the privacy and security of transmitted data. Encryption algorithms manipulate bits according to complex mathematical rules, transforming readable data into sequences of bits that appear meaningless to anyone without the correct key. When the data arrives, the recipient uses the key to reverse the transformation and restore the original information. In this way, bits not only represent the content of communication, but also the security mechanisms that keep it safe from interception or tampering. The universality of bits in communication becomes clear when considering the diversity of information that can be transmitted. Text, audio, images, and video are all reduced to sequences of bits before being sent. A phone call carried over the internet is broken into digital samples of sound waves, each represented by bits. A video conference combines bits representing video frames with bits representing audio streams, all traveling in real time. Even control signals, such as instructions to establish or end a connection, are expressed in bits. This universality makes the bit the foundation not only of data storage, but also of all forms of digital communication. The role of bits in communication also highlights the relationship between efficiency and redundancy. On one hand, systems strive to transmit as few bits as possible, using compression techniques to remove unnecessary data. On the other hand, they often add extra bits to ensure reliability and security. This balance demonstrates the flexibility of bits as a tool for both efficiency and robustness. Compression reduces the total number of bits needed to transmit a file, while redundancy ensures that errors in those bits can be detected and corrected. Together, these strategies ensure that communication is both fast and reliable. Ultimately, the transmission of data illustrates how the abstract concept of a bit becomes a practical element of everyday life. Each email sent, each web page loaded, and each video streamed is the result of countless bits traveling across networks at astonishing speeds. By understanding the role of bits in communication, one can appreciate the invisible infrastructure that sustains the digital age. Behind the apparent simplicity of a message appearing on a screen lies a complex system of encoding, transmission, verification, and reconstruction, all made possible by the smallest unit of data, the bit. One of the most remarkable aspects of bits and bytes is their ability to represent every form of digital content that humans use and create. Text, images, and sound may appear to us as entirely different forms of information, but in the world of computing, they are all reduced to sequences of zeros and ones. This universality of representation is what makes digital technology so powerful, because it allows the same machines and networks to handle vastly different types of content without needing separate systems for each. By exploring how text, images, and sound are represented using bits and bytes, we can understand how the richness of human expression is captured, stored, and transmitted in digital form. Text representation was one of the earliest uses of bits and bytes in computing. Each character, whether a letter, number, or symbol, is mapped to a specific numerical value. This mapping is known as character encoding. One of the earliest and most influential encoding systems was ASCII, the American Standard Code for Information Interchange, developed in the 1960s. ASCII used 7 bits to represent characters, providing 128 possible codes. This was sufficient to cover the English alphabet, digits, punctuation marks, and control characters such as line breaks. Later, as computing expanded globally, ASCII was extended to 8 bits per character, creating 1 byte per symbol and allowing for 256 possible codes. Still, this was not enough to capture all the writing systems of the world, which led to the development of Unicode. Unicode is a universal standard that assigns unique codes to characters from virtually every language, along with symbols, emojis, and other marks. Unicode relies on multiple bytes per character when necessary, demonstrating how flexible the byte system is in scaling to human diversity. Images present a different challenge because they are visual rather than symbolic. To represent an image digitally, it is divided into a grid of pixels, where each pixel represents a single point of color. The color of each pixel is encoded using bytes. For example, a simple grayscale image may use 1 byte per pixel, with values ranging from 0 to 255, where 0 represents black, 255 represents white, and the values in between represent shades of gray. For color images, more bytes are required. The most common system uses 3 bytes per pixel, 1 for red, 1 for green, and 1 for blue. By combining these 3 primary colors in varying intensities, millions of colors can be represented. A single image may therefore require millions of bytes, depending on its resolution. Compression techniques, such as JPEG, reduce the number of bytes needed by removing details that are less noticeable to the human eye, but the underlying principle remains that every image is just an organized collection of bytes describing pixel colors. Sound representation is equally fascinating, because sound is a continuous wave in the physical world, while computers can only handle discrete values. To bridge this gap, sound is digitized through a process called sampling. The sound wave is measured at regular intervals, known as the sampling rate, and each measurement is assigned a numerical value that represents the amplitude of the wave at that moment. These values are then encoded into bytes. A common standard for high-quality audio, such as that used in compact discs, is a sampling rate of 44,100 samples per second, with each sample represented by 16 bits, or 2 bytes. Stereo sound doubles this amount, since 2 channels must be stored. The result is a large number of bytes per second of audio, which is why uncompressed sound files are very large. Compression formats, such as MP3, reduce file sizes by discarding frequencies that are less audible to humans, but the representation of sound remains fundamentally a sequence of bytes encoding sampled amplitudes. The ability to represent text, images, and sound in the same basic framework of bits and bytes also allows these forms to be combined. A web page, for instance, may contain text, images, and embedded audio or video. But to the computer, it is simply a collection of bytes organized in a particular structure. The universality of bytes ensures that these different media can coexist and be transmitted together over the same networks. This convergence is one of the defining features of digital technology, allowing us to create multimedia experiences that combine different forms of human expression seamlessly. Another important dimension of representation is error detection and correction. When bits representing text, images, or sound are transmitted, they may be subject to noise and errors. To preserve accuracy, extra bits are often added for redundancy, allowing errors to be detected and corrected. For example, in text transmission, a corrupted byte might change a letter into a meaningless symbol, while in image transmission, a corrupted byte might alter the color of a pixel. In sound, corrupted bytes might result in pops or distortions. Error correction ensures that these issues are minimized, preserving the fidelity of the original content. Compression also plays a central role in the practical representation of text, images, and sound. Text compression techniques, such as Huffman coding or dictionary-based methods, reduce the number of bytes needed to store repetitive patterns. Image compression algorithms, such as JPEG or PNG, exploit redundancies in pixel data, while audio compression formats, such as MP3 or AAC, reduce storage by approximating sound in ways that the human ear perceives as nearly identical. These techniques highlight the balance between efficiency and quality, demonstrating how bits and bytes can be manipulated to achieve different goals depending on the application. What unites text, images, and sound is that all of them can be reduced to patterns of bits and bytes, which machines can store, process, and transmit. This reduction does not diminish their richness, but instead enables them to be shared globally, duplicated endlessly, and integrated into new contexts. The universality of bits and bytes as a representational system is therefore one of the greatest achievements of computer science. It allows humans to express themselves in digital form without being limited by the underlying machinery, because the translation from human expression to binary data is automated and standardized. Ultimately, the representation of text, images, and sound illustrates the extraordinary versatility of bits and bytes. They are not bound to a single type of content, but can be adapted to capture the full range of human communication and creativity. Whether a simple text message, a high-resolution photograph, or a symphony recording, everything reduces to the same fundamental units. This shared foundation makes possible the interconnected digital world we live in, where diverse forms of media are stored on the same devices, transmitted over the same networks, and combined into rich experiences. By understanding how text, images, and sound are represented with bits and bytes, we gain a deeper appreciation of the simplicity that enables complexity and of the hidden unity underlying all digital information. In today's digital age, bits and bytes have moved far beyond the abstract or theoretical level and have become the very foundation of modern life. Every digital service, from social media platforms to online banking, from streaming entertainment to advanced scientific research, is powered by the manipulation of immense quantities of bits and bytes. The rise of what is commonly known as big data has brought about both unprecedented opportunities and daunting challenges. Big data refers to the massive volumes of data generated every second by billions of devices, sensors, and human interactions worldwide. This data is measured in terabytes, petabytes, and even exabytes, illustrating how the language of bits and bytes has scaled to unimaginable levels. Understanding how bits and bytes function in these contexts is essential to appreciate both the promise and the difficulties of the modern digital landscape. One of the most prominent applications of bits and bytes in the era of big data is online communication and social media. Every message sent, every image uploaded, and every video shared is composed of bytes traveling across global networks. Platforms like Facebook, Twitter, Instagram, and TikTok manage trillions of bytes daily, storing them in massive data centers. These centers are vast warehouses filled with servers, each containing countless memory chips and storage devices that organize and retrieve bytes at incredible speeds. What makes this possible is the standardized structure of data in bytes, which ensures that information from diverse sources can be stored and retrieved consistently. Another modern application is streaming media, which depends heavily on the efficient transmission of bytes. Services like Netflix, YouTube, and Spotify deliver movies, shows, and music to billions of users. Each video is essentially a sequence of compressed bytes, representing frames of images and samples of sound. To deliver these seamlessly across networks, enormous amounts of data must be transmitted per second. This requires compression algorithms that reduce the number of bytes without sacrificing too much quality, as well as high-speed networks capable of transmitting gigabits per second. For the user, this results in a smooth viewing or listening experience. But beneath the surface lies the ceaseless movement of billions of bits. Scientific research also relies heavily on big data. Fields such as genomics, astronomy, and climate science produce vast data sets that cannot be processed without advanced computing systems. Sequencing a single human genome, for instance, generates hundreds of gigabytes of data, all encoded as bytes. Observatories studying the universe capture petabytes of images and measurements, while climate models simulate decades of weather patterns, producing enormous amounts of numerical data. In each of these cases, the ability to handle large quantities of bits and bytes determines the success of the research. Without powerful storage systems and processing capabilities, such projects would be impossible. Yet with these opportunities come significant challenges. The first challenge is storage. As the volume of data continues to grow, finding ways to store it reliably and affordably becomes increasingly difficult. Traditional hard drives and even solid-state drives, while impressive, struggle to keep up with the exponential growth of data. Companies and institutions invest in large data centers that consume vast amounts of energy to keep servers running and cool. This raises environmental concerns, as the energy consumption associated with data storage contributes to global emissions. The challenge is not only technical, but also ecological, forcing researchers and engineers to develop more energy-efficient ways to handle bits and bytes. The second major challenge is transmission. Moving large quantities of data across networks requires immense bandwidth. For instance, streaming services must deliver content to millions of users simultaneously, while research institutions must share petabytes of data across continents. Even with advances in fiber optic technology and wireless networks, bottlenecks still occur. Latency or delay remains a persistent problem, especially for real-time applications like online gaming, video conferencing, and remote surgery. In these cases, even a slight disruption in the flow of bits can have noticeable consequences. Overcoming these transmission challenges requires both infrastructure investments and new technologies to optimize the flow of data. Another critical challenge is security. Bits and bytes, once transmitted, are vulnerable to interception and manipulation. Cyber attacks exploit weaknesses in systems to steal data, corrupt files, or disrupt communication. encryption has become a standard practice, transforming bits into encoded forms that are meaningless without the proper key. However, as attackers grow more sophisticated, encryption methods must evolve to stay ahead. The sheer scale of big data also complicates security, as monitoring billions of bytes for threats is no simple task. Ensuring the integrity and privacy of data in the digital age is one of the most pressing issues facing individuals, companies, and governments alike. A further challenge is interpretation. Collecting massive amounts of data is not useful unless it can be analyzed and understood. This is where artificial intelligence and machine learning come into play. These systems process vast data sets, searching for patterns and insights. For example, AI models trained on millions of bytes of medical images can assist doctors in diagnosing diseases. Algorithms analyzing social media data can predict trends or detect misinformation. However, this reliance on data also raises ethical questions. Biases in data can lead to unfair outcomes, while the sheer scale of surveillance made possible by big data threatens privacy and personal freedom. The challenge lies not only in managing bytes, but also in using them responsibly. The era of big data also highlights the tension between efficiency and redundancy. On one hand, compression techniques aim to reduce the total number of bytes needed to represent information. On the other hand, redundancy is added to ensure reliability, such as backup systems and error correction codes. Striking the right balance is essential to ensure that data is both manageable and trustworthy. For individuals, this balance appears in everyday life when deciding whether to store photos in compressed formats to save space or in uncompressed formats to preserve quality. For organizations, the stakes are much higher, as decisions about how to manage bytes can affect both performance and reliability on a global scale. Ultimately, the modern applications and challenges of bits and bytes in the era of big data illustrate both the triumph and the complexity of digital technology. From entertainment to science, from communication to security, everything we do relies on the constant movement and transformation of bits. Yet as data grows at exponential rates, the limits of storage, transmission, and interpretation become increasingly evident. The future of computing will depend on finding new ways to manage these challenges, whether through more efficient hardware, smarter algorithms, or entirely new paradigms, such as quantum computing. What remains clear is that bits and bytes will continue to be at the heart of these developments, shaping the digital world we live in and the possibilities we can imagine. As we reach the conclusion of this exploration into bits and bytes, it becomes clear that these tiny units of digital information are not just abstract symbols, but the very foundation of modern computing and communication. From the earliest ideas of binary numbers proposed by Leibniz to the mathematical formalization of information by Claude Shannon, the bit has evolved into a universal concept that underpins the entire digital world. Grouped together as bytes, these small units allow for the representation of text, images, and sound, the operation of software, the storage of knowledge, and the transmission of information across global networks. The story of bits and bytes is therefore both a historical journey and a technological triumph, revealing how simplicity can give rise to extraordinary complexity. The significance of bits and bytes in the present day cannot be overstated. Every digital device, from the smallest smartwatch to the largest supercomputer, depends on them. They are the invisible language spoken by machines, silently enabling billions of interactions every second. When we send a message, watch a film, or listen to music, we rarely think about the fact that we are engaging with nothing more than carefully structured sequences of zeros and ones. Yet without these sequences, none of the conveniences of the digital age would exist. The byte has become the standard unit for measuring memory and storage, shaping our understanding of file sizes, network speeds, and system capacities. Its practical meaning is woven into our daily vocabulary, making bits and bytes part of everyday life, even if their technical details remain hidden from most users. Looking to the future, the role of bits and bytes will remain central, though the ways in which they are used may change. One of the emerging frontiers is quantum computing, which introduces the concept of the quantum bit or qubit. Unlike a classical bit, which must be either 0 or 1, a qubit can exist in a superposition of states, effectively being both 0 and 1 at the same time. This allows quantum computers to process information in radically different ways, offering the potential to solve problems that are intractable for classical machines. While quantum computing is still in its early stages, it represents a possible evolution of the bit, demonstrating that the concept of binary information remains flexible and adaptable to new paradigms. Another area of future development is neuromorphic computing, where bits and bytes may be organized in ways that mimic the functioning of the human brain. Instead of relying solely on binary operations, neuromorphic systems may use spikes or pulses of activity to represent information, bringing computation closer to the way neurons communicate. These developments could lead to more efficient systems, capable of handling complex tasks, such as pattern recognition and learning, areas where traditional architectures sometimes struggle. Even in these innovations, however, the fundamental idea of reducing information to manageable, discrete states remains central, showing the enduring influence of bits and bytes. The challenges of the future also highlight the importance of bits and bytes. As the volume of global data continues to grow, storage and transmission must keep pace. Already, humanity produces more digital data each year than all previous centuries combined. Managing this information requires new approaches to compression, error correction, and data integrity. The balance between efficiency and reliability becomes more pressing as data reaches petabyte and exabyte scales. At the same time, concerns about privacy, security, and sustainability add further complexity. Each of these challenges must be met by refining the ways in which bits and bytes are stored, transmitted, and protected. Artificial intelligence and machine learning also rely heavily on bits and bytes. Training large models requires the processing of vast data sets, often measured in terabytes or petabytes. The representation of images, text, and audio as binary data makes it possible for machines to learn patterns and generate new outputs. The remarkable abilities of modern AI, from natural language understanding to image generation, are ultimately rooted in the manipulation of enormous numbers of bits. The efficiency of these systems depends on advances in hardware, where processors and memory chips handle billions of operations per second, all based on the simple switching of bits. This connection between the smallest unit and the most advanced applications illustrates the profound role bits and bytes continue to play. The cultural dimension of bits and bytes is also worth reflecting upon. They are not only technical units, but also symbols of the digital age. They represent the reduction of human creativity and communication into forms that machines can handle, allowing for the global exchange of knowledge and ideas. The fact that a song recorded in one part of the world can be instantly streamed on the other side of the globe is possible only because bits and bytes serve as the universal currency of digital exchange. In this way, they are as much cultural constructs as they are technical ones, shaping how societies interact and evolve in the digital era. Even as technology advances, the elegance of bits and bytes lies in their simplicity. By having only two possible states, they provide a solid foundation for systems of immense complexity. This binary framework ensures reliability, consistency, and universality. Every innovation in computing, no matter how advanced, continues to rely on this bedrock. Whether in the design of microprocessors, the architecture of storage systems, or the protocols of communication networks, bits and bytes remain the essential building blocks. In conclusion, the journey of bits and bytes is far from over. They have already transformed the world, enabling revolutions in communication, science, entertainment, and industry. Their future promises even greater possibilities, from quantum breakthroughs to brain-inspired architectures. At the same time, they present challenges that will require ingenuity, responsibility, and ethical reflection. By understanding the role of bits and bytes, we gain insight not only into the workings of machines, but also into the deeper nature of information itself. They remind us that the foundation of our digital civilization rests on the simplest of choices, the binary decision between 0 and 1, endlessly repeated and combined to form the fabric of the modern world.